Hello everyone, I'm Yumeng from University of Constance. Today I will present my paper, Reducing Ambiguity in Line-Based Density Plots by Image-Based Colorization. Here is our agenda. First, I will provide a brief description of the problem, followed by an introduction to our approach. Line-based plots, such as line charts or transportation route maps, are commonly employed for visualizing both time series and trajectories. High line volumes can result in visual clutter, impairing data perception. By using density instead of traditional lines, we create what we call a line-based density plot. This approach effectively eliminates visual clutter, bringing out the high-density patterns. However, line-based density plots do have their challenges. For instance, take a look at the temperature data on the left. In the highlighted area, you'll notice a zigzag pattern that can make it difficult to discern the exact path of the lines. Similarly, in the taxi trajectory data on the right, we primarily observe high-density patterns around the city main roads. This might give the impression of numerous taxis circling around the city center. To enhance clarity and reduce ambiguity, we introduce a colored density plot. By assigning similar colors to similar areas, we emphasize their resemblance and effectively minimize ambiguity. As you can see in these two colored density plots, the zigzag ambiguity on the left vanishes, and the ring pattern on the right becomes more distinct, breaking into multiple segments. Now I will introduce a related work. Some works have been devoted to presenting data in terms of density, including line data. For example, Lamp et al. Extend the kernel density estimation to curves, allowing the calculation of densities for line data. Hadley Wickham introduced a paradigm for visualizing large datasets called bin summarized smooth. This paradigm streamlines the process of creating density plots. Building upon this, Melitz et al. Applied the same paradigm to line data, leveraging GPU acceleration for rendering line-based density plots. These works provide the basis for our construction of line-based density plots. Prior research has recognized visual ambiguities and illusions. The principle of ambiguous data depiction introduced by Kinderman et al. Labels visualization lacking clarity as having confusers. Pomerang et al. Addressed the relationship between slope and line permanence in ghost clusters, proposing a slope-dependent density correction method to reduce visual errors. Hong et al. Examined the impact of size and lightness in scatterplots on perceived mean. However, there is currently no existing work dedicated to address visual ambiguities and illusions in line-based density plots. In the line-based approach, each line serves as a fundamental unit for clustering, abstraction, and querying. Curve box plot abstract line bundles in a box plot fashion. Streamline variability plots employ line clustering methods and construct curve box plots for each cluster. Time box queries data that traverses a box, indicating a range of positions within a specific time frame. Recently, Zhao et al. Introduced KD box, utilizing a KD tree to accelerate time box queries. The color map serves as a foundation for constructing our density plot. We adopt Genesis et al.'s perceptually consistent single-hue color map for density visualization with different hues. Additionally, Lu et al. Introduced Palatilar to enhance categorical colorization for perceptual consistency and category differentiation. However, categorical coloring methods used in multi-class spat plots do not convey the density information essential for our line-based density plots. Next, I will talk about the ambiguities in line-based density plots. Taking a scatter plot as an example, I will show the process of building density plots. First, we bin in the plots and then counting the number of points falling in each bin. After mapping the scalar values to colors, we get the density map for the scatter plot. For line plots, we take the same approach. The difference with scatter plot is that we count the number of lines touching each beam. Unlike a scatter plot, where individual points are isolated, lines in line-based density plots connect different beams, implying potential relationships between them. However, it's important to recognize that the perception of continuous patterns in line-based density plots is influenced by the Gestalt principles. In other words, the perceived pattern may not accurately reflect the underlying data. When investigating line-based density plots of real-world datasets, several patterns with ambiguities are found. We grouped them into three basic types. Illusory patterns on the left, where a trend seems to be continuous but is created from diverging data. Ambiguous continuation, where it is uncertain how a trend continues. And finally, disconnected clusters, where it's unclear if and how clusters are connected. To understand how users perceive these ambiguous patterns, we conduct a motivational, small-scale user study as detailed in our paper. To help reduce such ambiguities, we propose a novel coloring method for line-based density plots. Let's dive into our pipeline. I'll guide you through it step by step. First, within each beam, we don't simply calculate its density, we also extract its features, which we refer to as the feature set. Each beam corresponds to a unique feature set, containing identifiers of the lines that intersect with that particular beam. While we have constructed features for each beam, the number of beams can be overwhelming. To address this and streamline subsequent clustering process, we have identified key beam properties within line-based plots that allow us to reduce data volume through strategic sampling. Given that numerous beams share identical or highly similar feature sets, particularly those neighboring to each other, we can effectively curtail data by employing random sampling on selected beams. In high-density screen nodes, lines are closely clustered, while low density implies a more scattered arrangement. The feature sets of low-density beams are often subsets of high-density beams. To address this, we exclude some low-density beams from clustering, as high-density beams already cover their line identifiers. Next, using the sampled beams, we processed with the clustering process. We opt from average linkage hierarchical clustering because it's compatible with various distance metrics and doesn't require specifying the number of clusters in advance. Furthermore, the hierarchical tree we construct can be leveraged in subsequent interaction steps. For effective beam clustering in line-based density plots, we need a suitable distance metric for set-type data. Common choices like the Jakob index or Sorensen coefficient tend to produce lower similarity values when comparing sets of different sizes. As we aim for higher similarity when one beam is a subset of another, we prefer the overlap coefficient, which is insensitive to variations in set size. After constructing the hierarchical clustering tree, user can set cluster numbers or divide existing clusters. We determine the closest cluster for unsampled beams and employ circular multidimensional scaling for cluster color assignments. Our aim is to assign a hue value to each cluster, effectively mapping intercluster relationships to the hue view. To do this, we calculate the mean for each cluster. We use one-hot encoding to create feature vectors for beams, where 1 signifies the presence of a line and 0 denotes absence. These vectors enable us to compute cluster means. To map these means onto the hue view, we employ circular multidimensional scaling, optimizing angles through gradient descent to determine each cluster's hue value. Once we have the assigned hue for each cluster, we use these hues to create single hue color maps, which we then apply to color the clusters in our colored line-based density plot. Our colorization groups lines into beams, disconnecting individual trends. To align lines with clusters in the density plot, we propose a heuristic line filtering approach. We count the densities and the clusters of the beings each line traverses and select the cluster with the highest sum of densities as the line's designated cluster. This choice is informed by the fact that if a line frequently passes through a high-density area within a cluster, it's more likely to conform to the dominant train of that cluster. Now let's delve into results. In our temperature data, we can observe crossovers in area A, which are challenging to discern in traditional density plot. We confirmed these crossovers by examining the filter lines. In area B, our approach successfully eliminates the zigzag ambiguity. In the stock market data, we observe unconnected high-density patterns in areas A and B. The colorized density plot clarifies that these patterns are unrelated, and this is reinforced by examining the filter lines. Notably, the blue cluster predominantly consists of stocks listed after 2010 with higher prices, whereas the green clusters mainly comprises stocks with lower prices. In the traditional density plot of the zip trajectory data, we observe a U-shaped pattern in area A, which our colored results reveal to be an illusion created by multiple underlying patterns. In area B, lines appear to head in one direction but are grouped into different clusters, highlighting a limitation of our approach in accounting for factors like parallelism and other geometric line features. In the taxi trajectory data, the traditional density map suggests taxis circling around the Beijing city center, forming circular patterns. However, our colorized version breaks these circles. The lines associated with the green cluster rival taxis traveling via the airport highway to various locations in the city. Similar patterns emerge for other clusters. Taxis are less likely to circle a city center and are more likely to drive within specific parts of the city, indicating distinct travel patterns. In conclusion, we wrap up our paper. In this paper, we introduce a novel coloring method for line-based density plots. Unlike traditional methods focusing on line-based analysis, we aggregate lines into density plots and enrich them through image-based region clustering. In our current version, we employed a fixed bin size, which may not be ideal for less critical regions. Further work should explore optimized binning strategies. Additionally, while we have addressed three types of ambiguities in line-based density plots, we acknowledge that other ambiguities may exist. We plan to develop a comprehensive taxonomy for categorizing these ambiguities in the future. Lastly, our approach has the potential for extension to other chart types, such as parallel coordinates or scatterplot metrics. Thank you for your attention.